Now that we've learned how to work with vectors in terms of finding components or writing vectors in terms of magnitude and direction, we can start talking about motion in 2 dimensions. So objects, of course, do not always move in a straight line. A very common example would be throwing a ball or hitting a baseball or hitting a golf ball, and the ball moves through a parabolic path, moving both in the x direction and the y direction. So at any given moment in time, the position of the ball will have an x and y component. So x and y components of position. So we could write the position of this ball at any given moment as having an x component and a y component. Remember the I hat means specifically the x direction. J hat means specifically the y direction. Those are unit vectors. They have a length of 1, so they're considered a constant because they always point in the same direction and always have a length of 1. If you remember back to linear motion, we said we could find the velocity of a particle at any given moment by taking the derivative of the position with respect to time. That is still completely true. So when we go to take the derivative of this position function, the derivative of the first piece, dx/dt, we would need a function describing the x position as a function of time to technically take the derivative. So we would take the derivative of that with respect to time. The I hat is a constant, so it just comes down with it. Similar to taking the derivative of 4x. The derivative would be 4 when we were taking the derivative with respect to x. So the I hat is a constant, so it remains in that portion. And then the derivative of this second piece, dy dt, j hat. So this represents the velocity of our particle or our object at any given moment in time. I hat means dx dt represents the x component of the velocity at any given moment in time. So we can find out the x component of a particle's velocity by taking the derivative of its x component of position with respect to time. Similarly, dy dt gives us the y component of velocity at any given moment in time. Acceleration. We know we can find acceleration by taking the derivative of the velocity with respect to time, which is the second derivative of position. So similar with the position, when we take the derivative here, the derivative of the x component of the velocity with respect to time gives us the x component of acceleration. The derivative of the y component of velocity will give us the y component of acceleration. So we know dv dt is our acceleration. This derivative of just the x component of velocity will represent the x component of acceleration. The derivative of the velocity with respect to time will give us the y component of the acceleration. So if you think back to vectors, when we were adding x components, we added to other x components to get an x component answer. It turns out even as we are looking at the calculus relationships, if we have a function that describes just x, meaning just the motion along the x-axis, that is independent from the y direction. So knowing a function that describes x will tell us specifically where the object is or the particle is at any given moment in time on the x-axis specifically. It does not tell us where it is on the y-axis. Similarly, having the function that describes y will tell us where the particle or object is at any given moment in time on the y-axis or in the y direction, but it does not tell us anything about the x. So x and y are still independent of each other. They are, of course, related in terms of the time, what time we are looking at, because we can only look at one moment in time. In the x direction, if we want to describe the velocity in the x direction, we simply need to take the derivative of the function that describes the x position. If we want the acceleration, we need to take the derivative of the velocity with respect to time of the function describing the x component of velocity. And again, this is the second derivative of the position with respect to time. So the really nice thing is the calculus relationships are still completely valid, but we are just needing to apply them individually for the x direction alone or for the y direction alone. If we want the function describing the velocity in the y direction, then we take the derivative of the function describing the y position. And similarly, the acceleration in the y direction, we take the derivative of the velocity with respect to time describing the y component of the velocity, which is also the second derivative of that position with respect to time. So the calculus relationships are still completely applicable, but we have to look at them in the x direction independent of the y direction, because those components are independent of each other. The only thing they have in common is the time at which we want to look at them. Now, in terms of having something like a constant acceleration, like we looked at in linear motion, it turns out since the acceleration in the x direction is determined by taking the derivative of the x velocity, x component of velocity with respect to time, we can say that the x component of velocity is equal to the integral of the x component of acceleration with respect to time plus, if you remember, this was the initial velocity, but it needs to specifically be the initial x velocity. In the assumption of having constant acceleration, we end up finding the velocity in the x direction at any given moment in time. The constant, we integrate, we get our constant acceleration times the amount of time that has passed, and then we still have that constant of integration. If we write it in this order, it's going to look somewhat familiar. We can put a final next to this Vx on the left. Final just meaning after so much time t has passed. We still find that the final velocity is equal to the initial velocity plus acceleration times time. Totally valid. But it's valid specifically using x components. So the x final velocity is equal to the x initial velocity plus the acceleration in the x direction times the time. Similarly, if we were to go through the same steps, so essentially substitute all the subscripts of x with subscripts of y, we would find that the final y component of velocity is equal to the initial y component of velocity plus the acceleration in the y direction times the time. So the kinematic equations we've been using are still perfectly valid, but they must be used and applied in one direction specifically at a time. We cannot put the total initial velocity that accounts for both x and y, so the magnitude, we cannot put the magnitudes in here because that's not accurately accounting for the components. When you look at the test notes, you're not going to see these two separate equations. Chapter 4 is on the same page as Chapter 2, and we have this kinematic equation already on Chapter 2. So they're not listed again. We just need to apply them in the x direction separately from the y direction. If we want to get to position, we know that the final position of an object, when acceleration is constant, it is equal to the initial position of the object plus the integral of our velocity with respect to time. Similarly to what we did with velocity, this is valid. We can totally apply this, but we have to look at x or y alone. When we were talking about linear motion, we found that this integral left us with this kinematic equation. Final position of an object or particle at any moment in time can be found if we know the initial position, initial velocity, time, and acceleration. In terms of two-dimensional motion, this equation applies, but it applies if I'm looking at just x components. So the final x position depends upon the initial x position, the velocity in the x direction initially, the acceleration in the x direction, and of course the time as well. The time is not specific to the x direction. If we were to solve this looking at y components, we would find the final y position depends upon the initial y position, the initial y velocity, and the acceleration in the y direction. Again, these equations are only valid if acceleration is constant, but we will have problems for sure where it is. So these sets of kinematic equations we've used before are perfectly applicable. When we think about the v final squared equals v initial squared plus 2a delta s, this equation is valid as long as we're looking at just x or y alone. So we could say that the final x component of velocity will equal the initial x component of the velocity squared plus 2x component of the acceleration times delta x. Keep in mind, delta x means x final minus x initial. Similarly, the equation can be used for y. Y components specifically. So essentially, we replace the x's with y's. So the kinematic equations, these three equations that we were using when we talked about linear motion, completely valid. We just need to know that the acceleration is constant. So it's nice in that regards that the relationship between position, velocity, acceleration is essentially the same. We just need to keep in mind that we need to look at x direction motion, independently of the y direction motion. And so we're going to do some examples, and we'll talk about a specific case called projectile motion, and we'll do that in the next couple videos.